Hello, everyone. Thanks for coming to this session. My name is Honghui Xiao. I'm from ByteDance, which is a Chinese company. I'm a Cisco certified inter-network expert. Meanwhile, I'm also an active developer in several open source communities like OpenStack and ONAP. In this session, I'm going to share a way of applying hardware offload to Kubernetes networks by using OpenStack. This is one of the benefits of combining the two most popular cloud platforms. Before we begin, I would like to take 1 minute to introduce our company, ByteDance. ByteDance is a technology company founded in 2012. Now we have a range of content platforms across languages, cultures, and geographies. In China, we have around 500 million of monthly active users with products like news aggregator app, Toutiao, and short form video app, Douyin. For markets outside of China, we launched TikTok, which is also a short form video app similar to Douyin. TikTok has quickly grown to the #1 downloaded app on Google Play and the App Store in multiple markets outside of China in 2018. So to meet the requirement of rapid growing business, multiple platforms such as Kubernetes and OpenStack are being used to provision various services. Okay, here is the agenda of this session. First, I will briefly go through Kubernetes networks. We will see how Kubernetes uses CNI, which stands for Container Network Interface, to manage its networks. Then I will introduce how Courier Kubernetes, which is an OpenStack project, integrates Kubernetes with OpenStack networking. With Courier Kubernetes, it is possible to choose to run both OpenStack virtual machines and Kubernetes containers on the same network. In most environments, OpenStack networking is based on OpenResearch. And just like every other software switch, OpenResearch compromises network performance. There are several ways to mitigate the overhead, such as DPDK, hardware offload, or even using a programmable hardware switch. So next, I will introduce one of the solutions, the OpenResearch hardware offload, and I will also introduce how it could be easily applied to Kubernetes through OpenStack. And last, I will share some test results of networking performance by running a simple topology over Flannel host network and OpenResearch hardware offload. So this is the content. Now we shall begin. First, let's see how container networking works. Let's start at a simple platform, Docker. The default network mode in Docker is bridge mode. In this mode, Docker will create a Linux bridge for each Docker network. When a container is created, Docker will also create a pair of base devices, one of which will be moved to the network namespace of the container, so it appears as the network interface of that container. The other one will be added to the Linux bridge that represents the Docker network. Since a pair of base devices act as a tuner, network packets of a container can be transmitted to the Linux bridge that represents the Docker network, and then send to other containers or even to the internet. This is basically how Docker networking works, and this is very much like the networking connection of virtual machines and physical machines. Things are a little bit different in Kubernetes. Kubernetes groups several containers as a pod. All the containers in a pod share a unique network namespace and a network interface. To simplify the management, an extra post container will be created along with the pod. And by default, Kubernetes also uses base devices and Linux bridge to construct its network. So as the picture shows, Docker networking and Kubernetes networking have some similarities. However, they use different networking plugins behind the scenes. Kubernetes is using what is called Container Network Interface. Let's see how Container Network Interface works in Kubernetes. Say we have a Kubernetes environment and have a controller and a worker node in it. Just like controllers in other platforms, the Kubernetes controller accepts users' requests and manages database. In the worker node, Kubernetes works as an agent that accepts commands from the controller and do the jobs. So when the Kubernetes API wants to create a pod, it will send the request to the Kubernetes agent on the worker node. After getting the command, Kubernetes will firstly create the post container and then inform the CNI plugin to create and configure networking for the pod. There are dozens of different CNI plugins out there. Although their backends and mechanisms are different, they do two same things, which are managing network interface and configuring networking for Kubernetes pods. CNI plugin could use anything to do its job. But to make things simple, we would stick to these devices and Latency bridge here. So when CNI plugin gets the command to create networking for a pod, it will create a pair of these devices. One waste device will be moved to the pod's network namespace as a network interface of containers in that pod. The other waste device will be added to Latency bridge, through which the pod is connected to the whole Kubernetes networks. This is similar to Docker networking, and many renowned CNI plugins work in this way. So this is basically how CNI works in Kubernetes. As an open interface, CNI plugin could be anything as long as it follows the CNI specification. So if there is a CNI plugin that can convert the CNI commands to OpenStack networking's operations, it is possible to use OpenStack networking as a network backend for Kubernetes. This is exactly what Kurio Kubernetes does. So let's see how Kurio Kubernetes can be a CNI plugin for Kubernetes. Kurio Kubernetes is an OpenStack Big Tent project, and this is a picture from a previous presentation in OpenStack Boston Summit 2 years ago. It perfectly depicts how Kurio Kubernetes enables native neutron-based networking in Kubernetes. The blue components in the picture belongs to Kubernetes. The green components in the picture belongs to OpenStack Neutron, and the yellow components in the picture belongs to Project Kurio Kubernetes. As you can see, there are two components in Kurio Kubernetes. The first one is Kurio Controller. Kurio Controller will watch Kubernetes API server whenever there are changes about pods, services, and endpoints. It will create, update, or delete corresponding Neutron resources by using OpenStack Neutron's REST API. OpenStack Neutron, on the other hand, might add some information to Kubernetes resources, for example, allocating IP address for Kubernetes pod. Those information is important for provisioning a pod. So Kurio Controller will also inject those information to Kubernetes by updating the annotation of Kubernetes resources. So Kurio Controller actually synchronizes data between Kubernetes and OpenStack Neutron bidirectionally. The other component of Kurio Kubernetes is Kurio CNI. It is yet another CNI plugin. So it will accept commands from Kubernetes and create network interfaces for Kubernetes pods. But unlike what we mentioned about these devices and Latency bridge, Kurio CNI creates a container network interface by using OpenStack's library. So the container network interface looks like an interface that an OpenStack virtual machine uses. And also there are some important information that has been injected to Kubernetes by Kurio Controller. So Kurio CNI will also get those information from Kubernetes API server and use them to configure the pod's network interface. So in this way, the network interface of a pod is created by Kurio CNI, and it is created by using OpenStack's library. And all its configurations are from OpenStack Neutron. So it has no difference with a normal OpenStack interface. As a result, the Kubernetes pod is connected to the OpenStack networking. Let's take a step further into Kurio Kubernetes. This is a picture from the document of Curio Kubernetes. It describes the workflow of how a pod's network is provisioned. When user creates a pod, the event will be sent to Curio controller and Kubernetes simultaneously, because they both have watched Kubernetes API. Curio controller will create a neutron pod for the Kubernetes pod. OpenStack neutron, when it receives the pod creation command, will allocate IP address and a MAC address for that pod, and then Curio controller will inject those information back to Kubernetes. On the other hand, Kubernetes, when it gets the Kubernetes pod creation command, will create containers and call Curio CNI to actually create pods networking. Curio CNI will use the information that Curio controller injects in Kubernetes to create a network interface and configure it accordingly. There is a notable sequence in this picture in the bottom, which is after the virtual network interface is created and configured, Curio CNI will wait for neutron pod to be active and then tell Kubernetes that pod networking is ready. The reason for that is only after neutron has set pod status to active, neutron has completed the configuration of virtual networks. And only at that time, the pod is possible to connect to the whole OpenStack networking. As we mentioned, there are two things that a CNI plugin should do. So in the case of Curio Kubernetes, managing network interface is done by Curio CNI, and the configuring networking for pods is actually done by OpenStack neutron. And the neutron pod's active status is a signal of readiness of OpenStack networking. Since Kubernetes pods have been plugged into OpenStack networking and there are already virtual machines there, so now we can build an environment that has both virtual machines and containers. And those workloads are connected to a unified networking. All the good features of OpenStack and Neutron are now available to Kubernetes. And the deployment could be really flexible. Like in this page, we have a node in the left only has OpenStack components and therefore can only host virtual machines. And we have the middle node only has Kubernetes and OpenStack Neutron and therefore can only host containers. And last, we have a node in the right that has OpenStack components and Kubernetes and therefore can host both containers and virtual machines. In most cases, the virtual switch used in OpenStack is OpenResearch. We can run overlay networks like VXLAN based on OpenResearch. But it is unavoidable to suffer from network overhead when using OpenResearch because it is a software switch. With VXLAN encapsulation and decapsulation, the performance is even worse. There are several technologies, for example, DPTK and hardware offload could somehow alleviate the loss in performance. Now we have run Kubernetes networks over OpenResearch by using OpenStack and Kubernetes. So it is possible to apply those acceleration technologies to Kubernetes network. Next, we will see how to apply hardware offload to Kubernetes networks. Let's see the mechanism of hardware offload before actually applying it. First, let's walk through how OpenResearch works. OpenResearch is based on OpenFlow and has been used in many software-defined networking systems. There are three major components in OpenResearch, which are OVSDB server, OVSResearchD, and OpenResearch datapath kernel module. OVSDB server is a configuration database which could be used to create or destroy OpenFlow switches, configure QoS and associate SDN controllers, and etc. Generally, it contains the durable state of OpenResearch. OVSResearchD receives OpenFlow flow tables from SDN controllers and instructs the kernel datapath about how to handle network packets. These two components are the control plane part of OpenResearch, and the OpenStack Neutron uses them to create logical network devices and logical network paths. If we divide a Linux server into several layers, we would have user space layer, kernel space layer, and hardware device layer. OpenResearch control plane, OpenStack Neutron, virtual machines, containers are all running in user space. However, the network interfaces of workloads are essentially in kernel space. Obvious kernel data path, as its name implied, is in Linux kernel space. So it is close to network devices. And it will receive packets first. And for the same reason, OpenResearch doesn't care about what workloads are running in user space. All it can see are some network devices. So we have a virtual machine and a container in this picture, and they are connected through OpenResearch. OpenResearch uses a mechanism similar to faster switching in hardware devices to forward packets. When OpenResearch kernel data path receives the first packet of a network connection, it actually doesn't know what to do with it, because all the OpenFlow flow tables are stored in OVS vSwitchD in user space. So as a default action, the kernel data path will upload the packet to OVS vSwitchD. In user space, OVS vSwitchD determines how the packets should be handled, then passes the packet back to the kernel data path with desired handling, and tell the data path to catch the corresponding instructions for subsequent packets. As a result, all the subsequent packets of the same network connection could follow the instructions in data path and just forward in kernel space. This way, a better performance than consulting OVS vSwitchD for every packet can be achieved, because context switching between user space and kernel space is expensive. OpenResearch kernel data path has been optimized several times, yet it is still being questioned for its low performance. There are several reasons for that, one of which is the context switching between user space and kernel space. When workloads in user space need to transmit data to virtual network interfaces in kernel space. Another common agreement is that there are not dedicated resources for OpenResearch kernel data path, because it has to share CPU and memory with other kernel modules. Based on our experience, the network overhead when using kernel data path is about 10% to 25%. There are some approaches aimed to provide better network performance for OpenResearch, such as DBTK and hardware offload. Let's see how hardware offload works. In hardware offload scenario, the OpenResearch data path is hopefully offloaded to hardware network interface entirely. Compared to OpenResearch kernel data path, there are several differences in the architecture. First is the virtual network interface of a workload. It has to be a SRV virtual function, which essentially resides in hardware NIC. This is because the data path is hardware offloaded to hardware NIC now, and virtual network devices should be in the same layer as the data path, similar to the situation of OpenResearch kernel data path. Since virtual network devices are virtual functions now, PCI pass-through is used to connect workloads and their virtual network interfaces. And therefore, the kernel is bypassed. So we don't have the context switching problem here, and the data path has its dedicated resources in hardware NIC. Another significant difference is there is a new component in the architecture, the Linux kernel traffic control module. Because OVS vSwitchD is in user space and the data path is in hardware device now, they need something in middle to communicate with each other. So in short, OpenResearch uses the TC module in kernel to instruct the data path in hardware NIC about how to handle packets. So it is still OVS vSwitchD that decides how to handle network packets. But this time, OVS vSwitchD will try to download the instructions to the data path in hardware NIC. And last, the obvious kernel data path is still required. Let's see how multiple data paths work in the OpenResearch hardware offload scenario. Again, when the first packet of a network connection is sent out, the hardware data path will receive it first because it is closer to network devices. But the hardware data path has no idea about how to handle the packets because OpenResearch only stores all OpenFlow information in OVS-VSHD in user space. So as a default action, hardware data path will upload the packet to OVS kernel data path. But the kernel data path also doesn't know what to do with the packet. So it will continue to upload the first packet to OVS-VSHD because this is a default action. In user space, OVS-VSHD determines how the packet should be handled and then tell corresponding data paths to cache the instructions for subsequent packets. But now there are two data paths, the kernel data path and the hardware data path. OVS-VSHD has to decide which data path to use to download the instructions. The decision depends on several things, such as OpenResearch's configuration, specific OpenFlow actions, hardware NIC's configuration, and the capabilities. If everything goes well, OVS-VSHD will download the instructions to hardware data path, and all subsequent packets are forwarded in hardware NIC directly without operating system getting involved. This is OpenResearch hardware offload. If anything says that hardware data path cannot handle the packet forwarding, OVS-VSHD will download the instruction to the kernel data path. And in this case, even if virtual network devices are VFs in hardware NIC, subsequent packet will be uploaded to kernel data path for forwarding. Because hardware data path doesn't have the instructions to handle those packets, and uploading to kernel data path is a default action. So in this way, as you can see, OpenResearch hardware offload works in a best effort way, and the kernel data path exists as a fallback solution. This is basically how OpenResearch hardware offload works. Next, let's see how to apply it to Kubernetes. OpenResearch hardware offload has been supported in OpenStack's Queen's release in Nova and Neutron, and it is available to virtual machines since then. Unfortunately, it has not been supported in Curio Kubernetes, so we need to enable it in Curio Kubernetes first. There are several things need to do. First, we need to create the network interface of a Kubernetes pod as a SRVVF because we want to use the hardware data path. Curio Kubernetes supports creating the network interface as a legacy SRVVF. There is a driver called VF SRV driver for it. But what we need is a little bit different. A legacy SRVVF is tied to a physical network, like a flat network or VLAN network. So it can be found through the corresponding physical network. In our case, we want to make the VF work in a VXLAN overlay network because there is a hardware data path in NIC which is capable of VXLAN encapsulation and decapsulation. So in our case, we need to find a VF from the hardware NIC that supports OVS hardware offload. So we created a new CNI binding driver for it. The code snippet in this page is from that driver, which finds available VF, sets the port namespace as the VF's namespace, configure it, and bring it up. The second thing we need to do is to add the VF representer port to OpenResearch. So what is a VF representer port? It is the configuration portal of a virtual function. In the case of OpenResearch hardware offload, we still need to let OVS-VSHD know how to configure virtual functions because they are logically bound to OpenResearch. But a VF is using PCI pass-through to bypass the operating system's kernel, so it is invisible to OpenResearch. and that's where a VF representer port fills the gap. After adding the representer port to OpenResearch, OVS can send corresponding commands to VF through the representer port. And fortunately, to do this job, we don't have to start from scratch. Because OpenStack has supported OpenResearch hardware offload, all we need are already there in the library os-vf. You can find more details in this GitHub repository. OpenStack Nova and Courier Kubernetes both use this library to plug and unplug virtual network interfaces. The problem is that Courier Kubernetes has not used that part of code, so we used it. We defined a virtual network interface in which the VF representer port is defined in port profile, and the virtual network interface is defined as a VIF host device. And the plugin of the virtual network interface is specified as OVS. And finally, the definition of the virtual network interface is passed to the plug method in the os-vf library to actually create the virtual network interface. So now we have created a SRV VF, moved it to the network namespace of Kubernetes pod, and added its representer port to OpenResearch. And last, we must use a pure OpenFlow solution. Because in the case of OpenResearch hardware offload, the kernel is bypassed. So all the stuff in Linux kernel, like IP tables, Linux bridge, are not available anymore. All we have is OpenFlow in OpenResearch. The fantastic feature of Courier Kubernetes is that it just bridges OpenStack Neutron with Kubernetes, while OpenStack Neutron can still have dozens of different networking backends. So when we need to find a pure OpenFlow solution, we have multiple options. We choose to use Dragonflow here. Dragonflow is also a Big Tent project in OpenStack. It is flexible, full function, and implements SDN in a distributed way. Most of its functionalities are based on OpenResearch and OpenFlow. I don't want to get into too much details about Dragonflow. It is a superb project and perfectly fits our requirement. You can find more details in this GitHub repository. By using Dragonflow, the virtual networks are implemented as OpenFlow flow tables in OpenResearch, and therefore are able to be offloaded to hardware NIC. So now the VF in hardware NIC has been moved to the network namespace of Kubernetes pod. The VF representer pod has been added to OpenResearch, and the pure OpenFlow solution provides the possibility of OVS datapath hardware offload. So we have brought the OVS hardware offload to Kubernetes pods by using Courier Kubernetes, OpenStack Neutron, and Dragonflow. Okay, next, let's see the network performance of hardware offload in Kubernetes. We test the network performance in a simple environment. Two hosts are connected under one switch. The bandwidth is 25 gigabits. The hardware and the software of hosts are listed. I don't want to go through all of them, but there are several things need attention. The first is that we use Verilog CX4LX as physical NIC because it supports OpenResearch hardware offload. I saw there is a Verilog booth in the marketplace, and there are more fancy network interface cards there, so you can find more details there. And the second is the version of OpenResearch. It has to be greater than 2.8 because that's when the TC flow offloaded feature is supported. The third is that we need to use OpenStack after Queen's release because that's when OVS hardware offload was supported. We created a simple topology in Kubernetes for testing. A pod was created at each host, and we ran a set of tests several times over different network configurations. In the first case, we use Flannel as the Kubernetes CNI plugin. Flannel is a simple and also popular CNI plugin based on Linux Bridge. We used it in its VXLAN mode, so the pod network was actually a VXLAN network in this case. In the second case, we use Courier Kubernetes as Kubernetes CNI plugin and applied all the hardware offload stuff we just mentioned. Meanwhile, we didn't want to lose the flexibility of overlay network, so we also create a VXLAN network here. In the last case, we created pods in host network mode. So it is underlay network between Kubernetes pods. This case has the best network performance that Kubernetes pods can achieve. In the first test, we use iPerf to test the throughput. iPerf servers are running in one pod, and the iPerf clients are running in the other pod. We increased the number of connections by adding more iPerf servers and clients. The result is in the picture. As you can see, Flannel has a significantly lower throughput. On average, it has 30% lower throughput compared to host network. On the other hand, when applying Courier Kubernetes and obvious hardware offload, the throughput is just 3% lower compared to host network. And please note that it is a VXLAN network between pods in hardware offload case, and in host network case, it is a flat underlay network between pods. The reason why there is still a 3% loss in throughput when applying hardware offload is probably because of the first packet, which has to be uploaded to OVS VCT in user space. Another possible reason is the 50 bass overhead that VXLAN brings in network packet header. Next, we use NetPipe to test the latency. We use the small packets in this test, so there won't be fragment of network packets. And the latency was calculated over 10,000 transmissions. So the impact of first packet could be omitted. For a single packet, the latency of Flannel is about 12 as host network, while the latency of OpenResearch hardware offload is identical to host network. So for the latency, thanks to OpenResearch hardware offload, Kubernetes pod has zero performance downgrade, even if VXLAN network is involved. The impact of VXLAN encapsulation and the decapsulation disappears magically. Last, we increased the size of messages. M2 was set to 1550, so as you can see, the latency grows when the size of message grows, because one network packet will be fragmented to several smaller packets. The horizontal axis in the picture is the size of network packets. As you can see, again, Flannel has the highest latency, while offload case has similar latency as host network. So it looks like a perfect solution with OpenResearch hardware offload. A Kubernetes pod in a VXLAN network can have similar network performance as it was in host network, while at the same time still has flexibility and the rich features come with VXLAN and software-defined networking. To wrap up, let's go through the pros and cons of this solution. For the advantages, first, this solution has great network performance. This is what we have been talking about in this session. Second, since OpenStack Neutron is the network backend for Kubernetes, it is possible to use a software-defined networking to manage Kubernetes networks. And the third, virtual machines and containers are connected in a unified network. There are also some disadvantages. First is the limits of the number of VFs. The number of containers in a host could be more than the number of VFs. So some special schedule strategy should be considered. Second, the OpenResearch hardware offload is not as mature as OpenResearch kernel datapath. Some sophisticated obvious actions cannot be offloaded yet. And due to the limitation of TCAM in physical devices, the network connection in hardware datapaths cannot be as many as there are in kernel datapaths. And the third, just like every kernel bypass approach. Traditional tools based on Linux kernel like TCP dump, BPF are not available anymore. So this is about using OpenStack to provide a hardware offload network for Kubernetes. And anyway, I think it is a promising feature. Okay, that's all I have. Thanks for listening, and any questions?
Can I change to use Intel VCAR?
You mean Intel's network interface, right?
Intel VCAR.
As far as I know, Intel has the network interface card can support obvious hardware offload, but it has not on the market yet. So you can use it as long as Intel has this kind of card.
Do you need Mellanox EF drivers in the box?
I'm sorry, I cannot hear you. Could you walk to the microphone? You mean the network interface driver? It should be in the latest Linux kernel now, like in 4.14. Linux kernel 4.14 has the driver, so we don't need to install it explicitly.
So all the pods that you have tested in the host and the family and the offload, the pods are the same, or are the pods being specific for each test deployment? Normally in VMs, you need to have Mellanox virtual function driver inside the VM in order to make the SRE work. So I'm just curious.
Yeah, I get you. Yeah, in the beginning of our test, we still need to install the drivers in a Fedora, for example, to support the VF of Mellanox. But in the latest Linux kernel, it appears that the driver is integrated in the Linux kernel. So I guess if you use the latest kernel, you won't need to install the driver now.
Is this working? Yeah, okay. So, hi. My name is Daniel Mellado. I'm the Kubernetes PTL. I've been there for a couple of cycles. And I have a couple of questions regarding your solution. So first of all, thanks for spending time on this. And I hope that you'll be able to contribute it back. And I'll be happy to review and help you doing so. So regarding the testing, yeah, if I understood correctly, you're just running pods and running iPerf and netperf, but you're not covering any kind of services. Do you plan to handle the services there too? Because that documentation that you were showing is a little bit outdated. So we used to support LVAS version 2. We no longer do so at all. And also, this is going to work. You didn't cover the query daemon case. Secondly, also, like, I don't know if you plan to go, I mean, regarding the testing, I don't know if you were just covering the flat solution where Kubernetes stands on one side and OpenStack on the other one, or if that was done using the nested, I mean, having Kubernetes running on top of OpenStack VMs. And I'd be interested in getting to know that. I don't know if that would take maybe too long, and if it's so, I'm happy to speak with you offline.
For your second question, we run OpenStack and Kubernetes separately. We don't run Kubernetes inside OpenStack virtual machines. Because now we just use Kubernetes as some sort of lightweight virtual machine. We run services in Kubernetes pods, and we just moved the services that was used to run in the virtual machine to Kubernetes for convenience.
But I mean, when I'm speaking about services, I mean Kubernetes service, which we do map to OpenStack load balancer. So whether you're using just Neutron LVAS version 2 or Octavia, or what kind of, or you just didn't cover that part.
Oh, you mean Kubernetes services, right?
Yeah.
Yeah, this is a great question because current Kubernetes use Octavia as Kubernetes services, but that kind of part cannot be uploaded to the hardware NIC because it is based on namespace or even based on virtual machine. So for now, we just use port networking. It can be uploaded to hardware NIC completely, but for services, it could be uploaded to the hardware NIC as long as you use the OpenFlow group action. But the group action it cannot support the full functionality of a load balancer or Kubernetes services. So yeah, this is kind of the gap for the solution. And I should put that to the disadvantages.
Mm-hmm. In any case, I'll be happy to help you get this upstream because I think it's interesting. So thanks for that, guys.
Well, first of all, and thank you for a very, very interesting talk. That was amazing. What I'd like to ask is, you might correct me here, but on the Mellanox LX4s, I think you're limited to about, I think it's 250 SRILVs. What do you do? Is there some sort of fallback path if you run out of VFs, if you create more pods than say 250 per hypervisor, or like how do you, or do you just say, okay, we can't create any more pods on this?
So do you mean there is any loss in the fallback path?
Is there any way of, we can say, okay, we're going to dedicate the VFs to these particular pods, and then if we need to, if we need to add more pods, we can fall back to some other solution, or are we just stuck at this hard limit?
Let me review your question because I'm not sure I totally understand you. So you mean, is there any solution for the fallback path that in case the data path cannot be offloaded, right?
Yeah, if you've got limited capacity on the hardware, like you can only handle so many VFs, right? So you've got what happens when you hit that limit?
Yeah.
Can you fall back somehow to some other method?
Yeah, this is also a great question because this is what we've been trying to solve in a real environment. So for specific network interface card, the supported offloaded actions are certain. So we need to orchestrate our OpenFlow flow tables that make sure that they can all be offloaded to hardware NIC. We will not allow the fallback solution happen if we really want to use the hardware offload solution. And in case there are any fallback happened, so we also tested that the performance is similar to obvious current data path. So we think it is not a big deal. So we just put it there and firstly let it make sure it can be offloaded, and then if it cannot be offloaded, it is not a big deal for us.
Okay, thank you.
Okay, thanks everyone.